All right, let's get right into it. Today, we're going fundamental. We're going to try and decode the basic operating system of our universe. Yep, the rules of motion. These are the rules that govern everything from a baseball flying through the air to planets circling the sun. So, let's get started. What's so incredible about this is that we didn't invent these rules. They were always here. For thousands of years, we've just been slowly, carefully learning how to read them. It's like we stumbled upon the instruction manual for reality itself, and we're finally starting to understand the language. So, a task that huge, where do you even begin? Well, you start with the basics. You have to learn the language of motion, one piece at a time, and that is exactly what we're about to do. So here's our roadmap. We'll start by figuring out how to describe where something is, using distance and displacement. Then we'll see how fast it's going with speed and velocity. After that, we'll explore how that motion changes with acceleration and dig into why it changes with force, mass, and weight. And finally, we'll bring it all home with Newton's three incredible laws of motion. Okay, first up, let's tackle something that trips a lot of people up. We're going to use a simple road trip to clear it up. See, distance and displacement are all about answering two very different but very important questions about any journey. So picture this. You're driving from city A to city B, but oh no, the main highway is closed. You have to take this long, winding detour. When you finally pull into town, you look down at your car's odometer and it says you've driven 150 kilometers. That total path you took, every single twist and turn, that's the distance. But what if a bird flew from your starting point to your destination? It would just fly in a perfectly straight line, right? Let's say that straight line is only 100 kilometers and it's directly north. Well, that's your displacement. It totally ignores your scenic route and only cares about the shortest, most direct path and the direction from where you started to where you ended up. So here's the key thing to remember. Distance is just a number. 150 kilometers. That's it. Physicists call that a scalar, but displacement is different. It's what they call a vector because it has both a number and a direction. So it's not just 100 kilometers, it's 100 kilometers north. That little difference is absolutely crucial for everything that comes next. And this whole idea of a simple number versus a number with a direction, it applies perfectly to our next set of concepts. Now that we know the difference between the path you took and where you ended up, let's talk about how fast you were going. Okay, let's imagine a new trip. You're driving for an hour and suddenly realize you forgot to pick up your friend. Ugh. So you have to turn around, go all the way back to get them, and then get back on the road. All that driving back and forth really adds up. Let's say in total your odometer says you drove 100 kilometers and the whole thing took you 2 hours. Your average speed is simply your total distance divided by your time. So 50 kilometers per hour. Now let's look at the velocity for that exact same trip. Even though you were driving like crazy for 2 hours and covered 100 kilometers, your final destination, your friend's house, was only 5 kilometers north of where you started. So your displacement is actually tiny, and your velocity is that displacement divided by time. So it's just 2.5 kilometers per hour north. You were really busy, but you weren't actually getting away from home very fast. So here's a super simple way to think about it. The speedometer in your car, that's telling you your speed. It just tells you how fast you're going. But to know your velocity, you'd need that speedometer and a compass, telling you which way you're headed. Speed is how fast, velocity is how fast and in what direction. Okay, let's be real. In the real world, we almost never travel at a perfectly constant velocity. We're always speeding up at a green light, slowing down for a stop sign, or turning a corner. And there's one single term in physics that covers all of these changes: acceleration. So the official definition is that acceleration is the rate at which your velocity changes. Now, it's not just about hitting the gas. Hitting the brakes is also acceleration. It's just negative acceleration. But here's the part that might surprise you. Simply turning a corner, even if your speed stays exactly the same, is also acceleration. Why? Because your direction is changing. And if your direction changes, your velocity changes. Just take a look at this. You've got a car and a big truck, and they're both trying to get to 60 kilometers per hour. The truck takes a full 30 seconds to get there, but the car, it does it in just 10 seconds. Because the car's velocity changes so much faster, we say it has a way higher acceleration. Simple as that.
So what on earth does a number like 5 meters per second squared actually mean? I know, it sounds super complicated, but it's not. All it means is that for every second that passes, the object's velocity goes up by 5 meters per second. That's it. So if you start at 10, after 1 second, you're at 15. After 2 seconds, you're at 20, and so on. It's really just the speed of the change in your speed.
So far, we've just been describing motion, where things are, how fast they're going, but now we get to the really interesting part. We get to ask, why? What causes an object to speed up or slow down in the first place? And to answer that, we need to get a handle on 3 connected ideas: force, mass, and weight.
Let's start with mass. This is a big one. Mass is just a measure of how much stuff, how many atoms, are inside an object. And here is the most important part. An object's mass never, ever changes. It doesn't matter if you're on Earth, the moon, or floating in space, your mass is your mass. It's part of you.
Weight, on the other hand, is a totally different story. Weight is not constant at all. See, weight is a force. It's the force of gravity pulling on an object's mass. And because gravity is different in different places, your weight can change. A lot. This table makes it super clear. Take a look at this 80-kilogram object. On Earth, its mass is 80 kilograms. On the moon, its mass is still exactly 80 kilograms. But its weight, whoa. On Earth, it weighs 784 newtons. But on the moon, where gravity is way weaker, it only weighs 130 newtons. Same amount of stuff, totally different gravitational pull. And this brings us to the grand finale. This is where everything we've just talked about, displacement, velocity, acceleration, force, mass, all of it comes together beautifully in Sir Isaac Newton's 3 laws of motion. These really are the foundational rules that run the show. Okay, Newton's first law. It's all about something called inertia. And put simply, it just means that objects are kinda lazy. They like to keep doing whatever they're already doing. If an object is sitting still, it'll stay still. If it's moving, it'll keep moving in a straight line at a constant speed forever, unless some other force messes with it. Just think about the Voyager spacecraft. It's been coasting through deep space for decades with its engines turned off. There's almost nothing out there to stop it, so it just keeps going. The second law gives us what is maybe the most famous equation in all of science. F equals ma. Force equals mass times acceleration. This little equation is basically the engine that drives motion. It tells you that if you push on something, it will accelerate. Want to make a really heavy thing accelerate really fast? You're going to need a huge force. For example, if you've got a 5-kilogram box and you want it to accelerate at 4 meters per second squared, the law tells you exactly what to do. Apply 20 newtons of force. It's just that simple and powerful. And last but not least, Newton's third law. For every action, there is an equal and opposite reaction. A rocket launch is the perfect example. The rocket's engine violently shoves hot gas down with immense force. That's the action. And in response, the gas pushes the rocket up with an equal and opposite force. That's the reaction. As soon as that upward push is stronger than the downward pull of gravity, you get liftoff. So there you have it, from the way a car turns a corner to how a rocket blasts into space. These fundamental principles describe the motion that makes our world work. And it really makes you wonder, doesn't it? If these elegant and pretty simple laws can explain so much, what other universal rules are still out there, just waiting for us to find them?